Jonathan Buttle with the California Department of Finance, Demographic Research Unit, and the topic is differential privacy and census data. I'm going to be doing a quick review of what it is, what differential privacy is, why the Census Bureau is looking to implement it for the 2020 census, the methodology behind it, how Census Bureau has implemented it to date in the demonstration data sets. We'll go through some examples of some of the data and kind of show how it's impacted that data. And then at the end of the last couple of slides, there's some links to some information if you want to dig into it a little more deeply. The Census Bureau has a lot of information posted on their website, and there's also folks outside of the Census Bureau that have also posted a number of analysis as well as data sets. Okay. So, why differential privacy? The Census Bureau cites two reasons for implementing it. Title 13 is the main reason that they cite, and it goes down to the fact that the law states that the Census Bureau shall not make any publication whereby the data furnished by any particular establishment or individual can be identified. They couple this with Title 5, which takes it a little further and states that any representation of information that permits the identity of a respondent to whom the information applies to be reasonably inferred by either direct or indirect means. So Census Bureau has taken a rather wide view of implementing these to ensure that the data that they put out there in terms of the census and as well as other data sets cannot be used to pull out demographic information about specific individuals. Okay, so the Census Bureau, in light of these mandates, went out and conducted a series of tests and simulations. Through these tests and simulations, what they decided is that their data protection techniques that they've used not only in prior censuses but also for the ACS were no longer sufficient to meet statutory confidentiality requirements. Specifically, the experiment that they used is they performed a reconstruction experiment. In that experiment, they were able to correctly identify the age, sex, race, and Hispanic ethnicity for an average of 50% of the persons in each of the blocks that they tested this on throughout the United States. Further, the Census Bureau then attempted to match the characteristics to an outside database in order to facilitate identification of specific people and found that only a small number of actual re-identifications were correct. Nevertheless, the Census Bureau concluded that the risk of re-identification is small, but they decided to go forward with differential privacy because they sensed that there was a threat that would only grow more strident in the future. Okay, so what is differential privacy? Well, differential privacy, the definition is it's a mathematical technique that allows for the formal quantification of the risk of data disclosure from a data set. Specifically, it's a property of an algorithm for answering queries. So if you have an algorithm and you use it in simply a set of instructions to go in and query a database and pull out a statistic, let's say the age ranges for people within a certain county. So that algorithm would be considered differentially private for a given level of epsilon if for two databases that differ by one record, it satisfies the equation. So basically it's a ratio of proportion. That's the technical definition. If the algorithm satisfies this definition, the expression then provides a bound on how much information can be inferred from adding or deleting a record in the database and prevents learning about a specific record by examining the two data sets. So in other words, what it basically does is injects enough noise into a data set so specific identification cannot be really done in any way, shape, or form. The theory behind this is also that it's future-proof. And that's really important with the Census Bureau because they wanted to ensure that in the future, people will not be able to go into past data sets and pull out information about specific individuals. So as a result, DP allows for quantifying the risk of identifying a specific element in a data set. It's basically a quantification. It's not necessarily a guarantee that this isn't going to happen, but it allows you to identify the risk and minimize it to the extent that you possibly can. And specifically, differentially private algorithms provide formal bounds as to how many queries can be made before the probability of learning specific information about a database increases beyond acceptable levels. This is important because what happens is when you're querying a database to pull specific information out of it, once you set the differential privacy parameters to it, you're limited to the amount that you can go past those initial parameters because you have to define your privacy parameters before you actually go in and utilize the algorithms. If you don't, if you subsequently perform more queries on the data set, then what you find is this actually reduces the amount of privacy protections put on the data set. We'll talk about that in a minute. Okay, so what are the components of differential privacy? Well, they include the privacy loss budget. The privacy loss budget is typically represented by epsilon. So epsilon covers a range. The privacy loss budget, when it's equal to 0, it basically means that the resulting data is pure noise. Privacy is 100% protected, but the expense of 0 accuracy. Likewise, if you have an epsilon that's very large, approaching infinity, the resulting data would basically allow for the full identification of any participants in the survey. In other words, you're looking at raw data. So what you want to do then is you want to have a value of epsilon somewhere between 0 and a large number in order to have a trade-off between accuracy and privacy. And so the values between 0 and infinity represent that trade-off between privacy and accuracy. Okay. So the privacy budget, sometimes known as the privacy loss budget. So it's an alternative interpretation of epsilon. And interestingly, if only a single query in the data is expected to be performed, that query might use up the entirety of a privacy loss budget. So if you have a data set and you go in and you only pull out the number of people in various age brackets for Sacramento County, and that's the only query you're ever going to do on this data set, then you can set the privacy loss budget at whatever you want to set it at, and it will pretty much stay there. You don't have to worry about it. On the other hand, and I mentioned this before, if you're performing a series of queries on data, it requires the allocation of the budget over all of the queries. Let's say you set the privacy loss budget on a data set to 4. Let's say you want to perform 4 queries on this particular data set. You want age brackets for a particular county. You want race ethnicity distributions. You want to know how many people live in houses and how many people are in GQs. Well, those are 4 different queries. If your total budget is 4, then each of those queries will take up 1/4 of the budget, or in this case, 1. Or you could set it within any range. The point being is that each of these queries has to, the sum of each of these queries, the epsilon has to sum to 4. Okay, so there are 2 methods of allocating the privacy budget, sequential and parallel. Okay, sequential composition. It's more or less doing a query on a single population or a single statistic. Now, this composition is where information from a data set is released on overlapping sets of individuals. And I'm sorry, I misspoke. So what this is if you're performing a series of queries that overlap. So let's say that for the County of Sacramento, you want to know the number of people in a series of age groups, and you also want to know the total population. Well, you're performing 2 queries on the same population. And so in this case, the total privacy budget is the sum of the privacy budgets for those overlapping queries. In other words, the analyst in this situation has to account for all the operations performed on the data to ensure that global privacy is preserved for that particular data set. This means it has to be planned out ahead of time. The analyst has to know which queries they're going to allow in the data set, and that influences how the differential privacy mechanism works. Parallel composition. Now this happens when there's a series of queries on a database that releases information on a disjoint set of individuals. So let's say you have a population database that covers 3 counties, Sacramento, Los Angeles, and San Francisco. So let's say you want to know the number of persons in each one of those particular counties. What this would mean for the privacy loss budget is the budget would be the maximum of each of those individual query budgets. So let's say you set one budget at 2, you set one budget at 3, and one budget at 1. The maximum of those would be 3. So the total privacy budget for that data set would be the maximum 3 of each of those individual queries. And the reason is because you're not having any interactivity among those particular populations. Even though they're in the same data set, you're querying different disjoint sets of populations, and so it allows you to do this, as opposed to running a query where you're repeatedly querying different characteristics on the same population, in which case it's the addition of the various privacy loss budgets for each of the individual queries. Okay. I mentioned before there's the privacy-accuracy trade-off. This particular graph illustrates what that is. It illustrates a comparison of the privacy loss between 1 and 6 and an accuracy measure. In this case, accuracy is defined as 1 minus the sum of the absolute differences of the noisy observations and the original observations divided by 2 times the length of the original observations. In other words, it's the L1 norm. There are other ways, of course, to define accuracy. Another way is to take the absolute difference divided by the total. There are different ways of measuring it. This is one way, but what you're looking at here is you notice that for smaller privacy loss budget, you're looking at very low amounts of accuracy, and you see that as the privacy loss budget increases, the accuracy increases, but at a decreasing rate. Interestingly enough, one of the things that you might have heard of if you follow differential privacy is if you look at some of the privacy loss budget numbers that were used in the 2010 DAS demonstration data set were all below 1. A number of them were below 1. Interestingly, when you graph that out, what you find is those accuracy numbers actually are negative, which means that you're in a situation where the absolute differences is actually larger than the denominator. So your error is actually compound at that point. Okay. So, differential privacy mechanism. The differential privacy mechanism works by injecting statistically calibrated noise into the data. The way the Census Bureau has implemented this procedure, what it does is it does a series of queries, pulls the queries out, and then adds a noisy term to that particular data to come up with what's called the noisy data. The amount of noise that's injected for each of these is determined by the epsilon and also by the sensitivity. Sensitivity is the amount that one or more individuals or records can influence the output of a particular DP mechanism. Normally for a count query, which is what the Census Bureau is running on the, or proposes to run on the 2020 census data set, is pretty much a count query. So you're looking at a sensitivity of 1. Sensitivity, however, changes depending on the type of query. So if you're not doing a count query, let's say that you're doing a query where you would be taking averages of household income, for instance, or personal income, or something along those lines, then what you have to take into consideration is that your sensitivity can suddenly at that point become the maximum amount of income that you have in your data set. If you know what that is, that's fine. You don't always know that, especially if you're talking about a data set that where some of the data is already perhaps masked or has been manipulated in some way. So difficulties can arise. We'll talk about that in a minute. So the Census Bureau has employed statistical noise derived from the geometric distribution. That's one of 2 distributions that is typically used in differential privacy mechanism. The other is the Laplace distribution. Both of these have 0 means, and they can have fairly long tails. The reason the Census Bureau uses the geometric distribution is because it has the advantage of returning integer values. values, where the Laplace distribution does not. In other words, it returns values that have decimal points. And so even though it's still considered differential privacy, of course, when you're outputting the counts from the noisy data sets, you want full integers. You do not want numbers that have any sort of decimal places on it, because when you go in to try to round those numbers, it actually causes certain problems and does slightly change the probabilities associated with the differential privacy levels that you've chosen for the engines. Okay. Post-processing. So what happens when the Census Bureau, in their engine as they have it running currently, is they take the raw data, they run the queries for whichever particular characteristics they're looking to pull out of the data. They run the noise mechanism on it. They get the noisy estimates out, and then they do what's called post-processing. Interestingly enough, post-processing is a characteristic of differential privacy, and it says that once a data set has been privatized through a DP algorithm, any additional processing on that privatized data set also maintains the differential privacy. So that's important, because one of the things that you find when you're running the noisy engine and taking a look at the results is you will have negative results. You will have negative numbers in the estimates that you get back. This especially becomes a problem for smaller jurisdictions like blocks, block groups, and even tracts in some cases, and even cities and counties. In some cases, if your epsilon is small enough, you can have a large enough noise, especially if it hits the far out tails of the noise distribution you're using, or that you have negative numbers. Post-processing is one way of dealing with that. What happens is they put it through a process where they set up a series of what are called invariants. In other words, what they do is they set up particular counts that are unchanged by the process. They are, in fact, the accurate counts, and then they tailor or tune the remaining data to those particular counts so that they add up correctly. So data processing can address not only counts less than 0, but it also can ensure that the sum of the counts of lower geographies are equal to the counts for higher geographies. So for example, the sum of the counts for all counties in the state are equal to the total count of the population for that state. Okay. So the Census Bureau has implemented differential privacy on a few different data sets. The earliest implementation was back in 2008, where they used an application called On the Map, which is primarily labor and household dynamics. They've recently implemented this for post-secondary employment outcomes, especially for earnings distributions. Now they are in the process of proposing utilizing this for the 2020 census. Keep in mind that the Census Bureau is not planning on implementing DP for the American Community Survey prior to 2025. There's a number of reasons for this, one of which is that the American Community Survey data set houses a lot more data characteristics and categories than does the 2020 census. There are a lot more tables derived from the ACS than there is from the decennial censuses. And in order to ensure that they're able to do this, there has to be more research done as to how they're going to implement it. So the Census Bureau is giving itself more time prior to attempting to implement it for something as complex as the American Community Survey. Okay. So differential privacy in the 2020 census. The original test implementation was on the 1940 census data set. This happened roughly around this time last year. What they did is they took the 1940 census data set, which was just recently allowed to become available for the public, and they utilized a prototype of their DP engine on this particular data set. Their methodology employs what's called a top-down methodology, where they start the nation and they go down for each particular geography. In this case, from the 1940 data set, because they're somewhat limited in the geographies, they use nation, state, county, and enumeration district. once they start with the top-down methodology, they create a histogram, basically a table of demographic attributes. In this case, total population, voting age, race, ethnicity, group quarters type. They assign them then to the they assign them back to the various geographies. Once that's done, they apply the noise through the geometric distribution mechanism. They apply the noise to the attributes. So by adding the results from the random number generator, geometric mechanism, to the attribute counts. And then they apply post-processing to the resulting noisy data, and they subject to what are called invariants. In this case, the invariants that they use, and by invariants, these are counts that do not change. They were the total population at the state level, and the total housing unit and group quarters counts at the block level, as well as using certain constraints on the process. So not only can you ensure that all of the totals for smaller geographies add up correctly to a larger geography, you can actually apply lower and upper bounds to the data. And so they also applied these bounds, and those were based on housing and population counts. Okay. Once that was done, and once the data sets were released to the public, there was a number of testing by various entities that went on to take a look at the results, look at it especially for accuracy, and to see what sort of distortions entered the data. So to precipitate this, the Census Bureau released the source code, which was scripted in Python, and the 1940 census data set was made available through IPUMS. So researchers could actually go in, assuming they had the correct licenses. One downside to this is that in order to perform the post-processing, because you're talking about a data set with 400 million entries, in order to perform the post-processing, you needed an industrial strength optimization program. In this case, the Census Bureau opted for Gurubi. They require you to have a license to run their software. So they made this out to the public for researchers who wanted to take a look at it. They also released a series of DP runs for various epsilon levels, 0.25, 0.5, 0.75, 1, 2, 4, and 6. And these were a series of 3 runs for each of these epsilons. So the analysis of the results found that there was for a low privacy loss budget, epsilon of 0.25, it resulted in significant distortions in smaller geographic areas and in attributes such as race, ethnicity relative to the original data. So the nice thing about this is you could go in and generate your own estimates and compare it with the estimates generated by differential privacy mechanism. The leader really for this, IPUMS and the Minnesota Population Center, David Von Ripper, really put together a number of presentations and analysis that was public about what he found. And actually, I have a link for that in the notes at the end of the presentation. So if you're interested in seeing what he came up with, his presentations are online and you can take a look at it. Okay. So the next step in the process was Census Bureau had the 2010 disclosure avoidance release later on in the year. So the 2010 demonstration data products is what this was called, and it was an updated differential privacy mechanism that was applied to the census edited file that was used to construct the 2020 census to generate person and housing tables from the PL94 as well as the SF1. The differential privacy process employed a global epsilon of 6. Keep in mind this was over 2 data sets, the person data set and the housing data set. So they allocated 4.0 epsilon to the person tables and 2.0 were allocated to the housing tables. In this data set, the geographies were expanded to include tract groups, tracts, block groups, and blocks, as well as nation, state, and county. So basically this was done along what's called the spine, and I'll talk about that in a second. The tables were expanded to include age by groupings, by sex, and households by race, ethnicity, sex, and the presence of persons over age 60. Okay. So there was a lot of analysis that went into this particular data set once it was released because it was actually using more modern data compared to the 1940 data set released earlier. Again, Minnesota Population Center really led the way with this, but there was also other analysis done by the National Conference of State Legislatures and others. And what they found is that there was a transfer of population counts from larger geographic areas to smaller geographic areas. This was a direct result of the construction of the invariance and the post-processing mechanism. There were significant distortions found in the demographic categories such as 5-year age groups. These distortions were also a lot more pronounced for smaller geographies than they were for larger geographies. There were distortions in population counts for American Indian and Alaska Native tribal areas, off-spline geographic areas. These particular areas, if you look at the graph on the right side, are those areas that are not included in the geographic hierarchy. So in other words, they would include places, county subdivisions, congressional districts, that sort of thing. Finally, there were distortions in housing statistics, vacant and occupied housing units, and especially in persons per household ratios. The reason for this is because the two data sets, the household data set and the person data set, were processed separately. They actually used separate differential privacy mechanisms for each of those data sets. So as a result, there was no post-processing applied to the counts such that the corrections were made on the housing statistics. And this, unfortunately, is one of the issues of differential privacy, is that trying to do join queries can lead to certain problems, especially when it comes to setting sensitivity and epsilon on the resulting data set. So the 2010 demonstration files. The Census Bureau heard these criticisms, attended a lot of the presentations, and they went back through and they looked at their methodology and they identified the following issues with their methodology. That measurement error was caused as a result of differential privacy noise. They also found, and probably more significantly, is that the post-processing area from creating internally consistent non-negative integer counts from noisy measurements, what actually tended to contribute a larger amount of the error than actually the measurement area resulting from the differential privacy noise that was injected to the data sets. And that's big because one of the things that you're trying to do with the post-processing is ensure that the data sets are actually going to be consistent and as accurate as possible internally. So in other words, your totals for lower geographies add up correctly to higher geographies. The problem is when you do this, what happens is if you have no control over certain other aspects of the data, what you find is that for negative numbers, especially for negative population totals for smaller geographies, it leads to a transfer of the totals from larger geographies to smaller geographies, which is one of the things that the analysts found when they looked at the data sets. Okay. This next slide is an analysis that I did. What I wanted to do is I wanted to take a look at just the noisy estimates. The Census Bureau analysis on the data sets that the Census Bureau has released has for the most part been done on the post-process estimates that were released. What I wanted to do is I wanted to take a look at the errors specifically before post-processing was actually applied to the data. As I mentioned before, the Census Bureau released all the code in Python that they utilized to generate these data sets. So it wasn't that much of a stretch to pull out certain pieces of it in order to go ahead and use it in a Python program. If anyone out there is interested in taking a look at that notebook, I'll be happy to share it. So the noisy estimates were generated using the geometric distribution engine from the 2010 DAS program. The original estimates were simply the county population counts drawn from the 5-year American Community Survey, the 5-year estimates. And the reason I use those is I want to be able to have all of the counts for all of the counties for each of the particular states. So what I found is pretty much along the lines of what other people found when they analyzed the resulting estimates that were released by the Census Bureau. Counties with smaller populations have a larger spread of errors than do counties with larger populations, and that when you look at these particular graphs there on the right side of the slide, what you see is that this particular distribution takes almost an inverted cone shape, where as the populations increase, the errors become smaller and smaller and smaller. And of course, a big part of the reason is simply because if you have a larger population, the errors that differential privacy assigns to each of these particular cells within a query doesn't change. It's consistent all the way across. For it's irrelevant what geography that you're using, it applies the same spread of errors to it. So if you have a relatively large population, say Sacramento County, it's going to have less of a relative impact on the spread of the errors than, say, if you have for Alpine County, which would find its estimates just completely destroyed. Okay. So the next thing I wanted to do is I wanted to compare 3 population pyramids for 5-year age groups taken from the 2010 DAS. I wanted to compare them for small population, mid-level population, and large population for 3 areas in California. The first of these is a compost CDP. The bars in the graphic in the light blue are the 2010 census with differential privacy as released by the Census Bureau, and the clear rectangles were actually the published 2010 census data. The population for this particular CDP is 341, and so what you see is a large amount of distortion introduced into this particular data set, pretty much so that these 5-year age groups are almost unusable. It zeroes out a number of age categories, including 30 to 34, 35 to 39, pretty much 75 and up are zeroed out. And you see large concentrations of population at 50 to 54, 60 to 64, 20 to 24, and 25 to 29. On the right, I included a chart to show what the absolute error was between the Census Bureau's estimate in the original 2010 census release and the 2010 census with the DP. And you see the absolute errors just by themselves don't look all that particular dramatic. They look fairly small, but when you take a look at what the actual graph looks like, because of the relative size of the populations in each of these age groups, it causes a dramatic amount of distortion. Okay, so the second is a mid-population, in this case Susanville. And I wanted to look at Susanville because you notice it has a significant budge in the male population between 20 to 24 all the way up really to about 60 to about 65. And this is because there's a major prison within Susanville City. So I wanted to take a look at how this distorted the data. Population for this particular, excuse me, for this particular city is 17,947. And what you see is while there are still distortions introduced, it's not nearly as pronounced as it was for the small population example. When you look at the absolute error for these particular estimates, what you find is that the absolute errors also have grown. They're larger. And this is a result, again, keep in mind that the noisy data doesn't really change. It's still taken from the same distribution. This is a matter of what happens with the post-process. Okay. And finally, the third one is a large population, in this case, Sacramento City. Sacramento City has a population of 466,000, at least it did as of the 2010 census. And what you see with this one is that there's still distortions, but the distortions are much, much less than what you saw in the previous 2 geographies. Also, the absolute errors have also grown. So the absolute errors for this particular city have also grown due to the size of its population. Again, one can surmise that this is because of the post-processing error injected. Okay. So Census Bureau is aware of these. They've taken a look and done the analysis themselves. They've heard what other people have said, and they've come up with, at least at this point, what they plan to do to improve the data accuracy. They're looking to revitalize or revamp how they set the epsilon. So they're looking to set an epsilon that reduces measurement error while still maintaining privacy. Remember back to that graph that I showed you. As the epsilon increases, the privacy loss also increases, but at the same time, the accuracy increases. So somewhere along that continuum is a way to pick that. there is research going in as to how one might go about doing it. I didn't really go into any detail in this. It's out there if you're interested in it, but it is one of the areas of interest in research that people are doing is there a way to quantify such that you pick a level of epsilon that allows you to maximize the accuracy for a given level of privacy? Okay, they look to revamp their post-processing mechanism. So now, instead of doing it all at once, they're looking to set up what's called a multi-pass post-processing. So it would be done in 4 passes. The first pass would compute the total population in GQ populations, the nation state level. The second pass would construct the measurements for the redistricting file, subject to the totals in the first pass. The third pass would construct the population estimates used in the population estimates program, subject to the first pass and second pass restrictions. And the final pass would be the rest of the demographics in the housing and the persons files, subject to the restrictions in the first pass, second pass, and the third pass. There are certain advantages to doing this in that it reduces some of the problems that you saw in some of the distortions introduced by post-processing. How much of that remains to be seen. In addition, the Census Bureau is updating their DAS development cycle. It's now consisting of a series of 4-week development sprints, followed by 2-week evaluation windows. During these 2-week evaluation windows, the plan, at least up to this point, is to release a series of metrics that the Census Bureau has derived to measure the accuracy of each of the subsequently released estimates. We'll talk about that in a minute. Okay. So the metrics tables. So starting in March of this year, the Census Bureau began releasing updated metrics tables. These were designed around use cases and stakeholder feedback. Their purpose was to allow users and stakeholders to see improvements in changes to the DAS mechanism. The metrics will include measurements of accuracy, bias, and outliers. And finally, the Census Bureau plans to add American Indian and Alaska Native, as well as off-spline geographies, to its processing and to improve race metrics and other outlier measurements. So again, the graphic there on the right shows the spline of the major geographies that Census Bureau uses, as well as some of the off-spline measurements. You'll notice that the American Indian and Native, Alaska Native is also considered to be an off-spline primarily through census blocks. So one of the complaints that has gone forward is that for small population areas, and especially for American Indian areas, that the distortions introduced are going to have a disproportionately negative impact on the statistics released. So the Census Bureau is trying to find a way to go about addressing that. Okay, so for the metrics tables, for the accuracy portion, Census Bureau has released the measurements of accuracy, and the way they measure the accuracy is by comparing the post-disclosure protected tabulations for each of the runs that they do to the original publicly available tabulations from the 2010 census and the internal pre-disclosure avoidance microdata from the 2010 census. The accuracy measures that they've released so far include mean or median absolute error, mean or median numeric error, root mean squared error, mean or median absolute percent error, and the coefficient of variation. Okay. They also have measurements of bias, and this is related to accuracy, but what this measures is the direction of change and whether it varies with population size or some other characteristic. Remember when we talked about post-processing, how it distorted the resulting statistics because it moved population from larger population centers to smaller population centers. Bias is one way of measuring that. So the proposed bias measures include median numeric error and median percent error, or what's called MALPI. Okay. So then this next slide illustrates the accuracy measures for population for counties all across the United States. The graph on the left is the most recently released, which was May 27th, And that's compared to the previous first release, March 25th, of the measurements of accuracy. So what you see is that the Census Bureau's published measurements of accuracy have improved fairly dramatically over what they released initially back on March 25th. You see that the mean absolute error is fairly consistent for each of the types of counties by population grouping, whereas if you look at it on the right, you notice that the mean absolute error actually grows fairly large for counties with total population over 100,000 or more. This is consistent with the old style of post-processing that the Census Bureau utilized when they initially released the DAS demonstration data set. You recall back to the three places that I compared with the absolute errors for those particular measurements. You notice that as the population size grew, the absolute error grew also. This is what you're seeing on the right. On the left, it shows that the mean absolute errors are fairly consistent. Same thing for the root mean squared error, as well as for the MAPE percentage and coefficient of variation. All of these are improved over what they published previously. The green, the fact that the numbers are in green in the May 27th table simply says that it was an increase in accuracy over 10% of what they had published previously. Okay, this particular table is the same, from the same measurements of accuracy as the preceding table. This, however, shows accuracy bias as well as outliers. The bias in this case is MALPI, and what this shows is that there is a slight reduction in population relative to the other populations for 1,000 persons and above. And when you compare it to the MALPI from the initial measurements that the Census Bureau released, you see that it is a fairly dramatic difference. You see that the populations actually increase, the MALPI increase for counties with total populations less than 1,000. And you can see as you go down that particular charts that the counties with total population of over 50,000 actually lost population. This again reflects what happens with the transfer of population from larger to smaller population. And then for the accuracy measures, or in this case outliers, you have the count of counties where the absolute percent difference is 5% to 10%. Those drop dramatically, and where the difference exceeds 10%, also dropping fairly dramatically. Which is great, but part of the problem is you're still not seeing how this is affecting distributions of data within certain particular statistics. They have released these particular measurements for, say, age groups for 5 years, for both place and counties, but you're still really, to confirm this, what you would need to do is actually see the data that's actually being released that these are based on. Okay, that's pretty much at this point the end of my presentation. So any questions, any discussion, anything people want to bring up? Okay, while we're waiting, I just want to measure really quick. So at the end of the presentation in the slides, I put down a number of links. I put down some links that have very accessible PDFs of the basics of differential privacy, links to Census Bureau websites that they, where they have the various pieces of information, releases. One of the things that they've started up is a newsletter for disclosure avoidance and differential privacy that you can subscribe to. You can find it there in the links. I've also have links to the GitHub Python repositories for anybody out there that wants to actually take a look at the Python source code. One of Census Bureau that was not actually developed by them, but actually was picked up by them and put on their GitHub page, which I think was a really good idea, is someone actually constructed a very simple introduction to differential privacy utilizing the methodology the Census Bureau has implemented initially. It's actually very accessible and can be run on using a very basic Python code setup. So I would definitely encourage anyone interested to check out the disclosure avoidance repository there at the bottom of the page. Additional resources, IPM's, David Van Ripper's analysis is online. I would highly encourage you to check that out. Also links to the 1940 full count data set. That particular data set is available if you want to use it. It's not for the faint of heart. It's got 400 million entries to it. It's huge, and it's not easy to deal with. The other thing is that NHGIS put up a series of tables that were derived from the 2010 DAS that were actually broken out by geography, both in wide format and narrow format. So if you're only interested in taking a look at a particular geography to see how these particular products fared, you can actually download just what you need at this particular link. Finally, the National Academy of Sciences, National Statistics had a December workshop where a number of presentations happened. That influenced a lot of what the Census Bureau is currently proposing towards their own changes in differential privacy. Both the presentations themselves and the materials are linked on those. So again, I would, if you have the chance, it's a really interesting view to check those out. So again, open to any questions or discussion.
It looks like we don't have any question from audiences.
Okay.
If you have any question, you can unmute yourself in this small group of amount. I think you can just, let me see. Oh yeah, just one chat.
Oh, sorry. Just like to thank everybody for tuning into the presentation. Appreciate you stopping by. The slides will be up at, I assume, SCAG's website once the workshops are over with. So you can go ahead and download the slides and take a look at any of the links that you might be interested in. Thanks.
Big round of applause to Jonathan. Thanks for excellent presentation. It was very informative, and it's a lot to take in with the information. Thank you, everyone. And as Jonathan mentioned, we are going to make the slide available on the website, and we look forward to seeing you next Thursday again.